Right. Okay. First, I'd like to thank the Sigma Psi folks for inviting me to give a talk, and to Aklesh for introducing me to the Sigma Psi chapter, or soon to be chapter at BHU. I've been a member of Sigma Psi since the mid 80s when I was in grad school. And I do enjoy their American Scientist magazine, and I've been to a few of their meetings. So given the fact that the audience comes from various different fields, it's a multidisciplinary area, I figured I'll talk about multidisciplinary topics. And one of my interests is in the history of science and history of optics and vision, to be more precise. And Ibn al-Haytham, or Al-Hazen, which is the Latinized form, is one of the founders of the field of optics. And in fact, the International Year of Light in 2015 was chosen so that it commemorated a number of important events in optics. And the first one was, of course, Ibn al-Haytham's 7-volume treatise called Kitab al-Manzir, which is the Book of Optics. So what I'm going to do is start out with, what do I mean by Arab or Islamic science, because it's not really Arab science, because it also included Jews and Christians and whatever. It was a multi-ethnic, multicultural process. And so let me go to the next slide. Okay. So, the problem is, oops, what happened? Okay, looking at, we usually say that hindsight is 2020. 2020 referring to the Snellen visual acuity, but we should probably say that it's diffraction limited. But why do we need to study history and how things developed? So by studying the past, we can know what mistakes were done, how we can prepare for the future, and also extrapolate into the future. And the typical time period I'm going to look at is during the Abbasid dynasty in Baghdad, which was around 800 Common Era to about 1100, when Arabic was the language of science. And as I mentioned before, it's not just Arabs. There were Persians, there were Jews, there were Christians. So there were a whole variety of people who were part of the scientific enterprise. Now, one would say, okay, yeah, sure. You're talking about Islamic or Arabic science. So where does religion fit into it? Of course, religion is a fundamental part of society at that time. And however, during the Abbasid era, there was a movement of rationalists who wanted to combine faith and reason. And in fact, if you look at the Quran, it says one must study the skies and the earth. And in fact, Muhammad said that to seek knowledge from the cradle to the grave, no matter how far that search took them, for he who travels in search of knowledge travels along Allah's path to paradise. Now okay. So, the Islamic Empire civilization was a great epoch, and the Muslim or Islamic scientists, philosophers, artists, and architects and others created a culture that still influences. And, the common view is that, okay, you had the Greek and Roman civilizations, then came the Dark Ages, and the Arabs, or they were caretakers of the knowledge of the Greek civilization, and then passed it on to medieval civilization. But that's not really true. They not only preserved ancient knowledge from the Greeks and the Romans, but they transformed much of it. And in fact, a lot of their work played a major part in the Renaissance and in the formation of later societies, including our present-day society. And of course, we all know about Islamic achievements in architecture, for example, the Qutb Minar, the Taj Mahal. Then you got the Rubaiyat of Omar Khayyam and the Arabian Nights and so forth. However, in terms of science, astronomy was a big aspect of Islamic science, and optics especially so. And so these are pictures from old manuscripts of various aspects of science that were being considered. And also the Islamic scientists got translations of manuscripts and scientific thought from the not only the Greeks, but also from the Indians and the Persians and Babylonian civilization, which they assimilated and systematized all of this. And especially in the areas of mathematics, medicine, astronomy, and optics. So one could say that this was probably the world's first truly international science. Now, unfortunately, most of us, or the way science is taught, we have a very, very Eurocentric view of science. So when we talk about optics, we talk about Isaac Newton. And of course, Newton well deserves the place of honor that he has. But however, even historians of science who acknowledge that Newton, before Newton, there were other scientists, do not go much beyond Descartes, Snell, and Kepler. But if you look at it, studies of catatropics and dioptrics goes back to the ancient Greeks, and this was really strengthened by the Islamic scientists. And I'm going to concentrate on theories of vision, because one of the major impetus for studying optics was, how do you see? How do you know what the world is around us? What is it about the eye that helps us perceive what is outside? And so this is very multidisciplinary because it brings in aspects of optics, brings in physiology, it brings in medicine and anatomy, it brings in cognitive science and so on. And I hope to give a little introduction to some of this, and especially work done by Haytham. So before we start, there were two major theories of vision. One was called the emission theory, which basically said that you see objects because rays of light or particles of light are emitted by the eye, fall on the object we are looking at, and illuminates them. That's why you see, and these light travels in straight lines. And in fact, if you look at it, Euclid and all called it as the fire within. And part of it, there's an interesting reason why they came up with it. It was because of ancient practice of Greek soldiers, covering their eyes, and also they knew that the eye was highly reflective because it's the light reflected back, which is your common red eye in flash photographs. And essentially, this was the extramission theory. The other theory was intromission, which is light reflects off objects and enters your eye. And so, but of course, the picture out here shows how rays of light come. This is from a medieval manuscript. Rays of light come from the eyes and illuminate the heavens above. And a more modern version is Superman with his X-ray eyes. But, so you can say that it's metaphorical, giving the geometrical relationship between the eyes and the objects. So, however, of course, you have the principle of reversibility of light. And in fact, this idea is used in modern computer graphics programs, which use ray tracing. What they essentially do is they trace lines of sight from the viewpoint to the objects and then to light sources to determine color and illumination. This is very common in modern computer graphics. And of course, this idea goes back to the extramission theory. But the intermission did not follow Euclid's geometrical model. And essentially, and this was championed by Aristotle, who said that the space between the object and the eye lights up so that the image of the object enters the eye instantaneously. Now, before I go further, one of the most important ideas come from the famous anatomist Galen, who was the first to dissect the human eye and come out with certain ideas about it, which we still use. Galen thought that your sight is because of what is called optical pneuma, which flows from the brain to the eyes through optic nerves, which are hollow tubes. And so he also described not only the retina, the light sensitive part of the eye, but also the cornea, the structure in front, which is responsible for almost 2/3 of the refractive optical power of the eye, and the crystalline lens, and also the aqueous and vitreous humors behind. And Galen said that the seat of vision was the crystalline lens. And he did not go much further than that. However, Islamic scientists between the 9th and 14th centuries produced a number of detailed treatises on ophthalmology and optics, which were influenced by the work of Galen, but also names like Al-Kindi and Ibn Ishaq, who was called Johannitus in Latin in the 9th century, favored the extramission theory of light. And in fact, some of the treatises they wrote were standard textbooks in medieval European histories. And so Al-Kindi is known as the philosopher of the Arabs. He was a polymath, like, for example, Thomas Young. He's called the father of Islamic Arabic philosophy because he synthesized, adapted, and promoted Greek and Babylonian philosophy in the Muslim world. But of course, in those days, philosophy was also science. Then Johannitus was an Assyrian of Christian descent, and what they did was they produced Syriac versions of classical Greek texts, and he also was a very productive translator of Greek medical and scientific treatises. So in that way, he preserved ancient knowledge for future generations. And in fact, this picture that you see in the lower, in the bottom part is really a picture of how we describe the eye to be. He wrote a famous book called 10 Treatises on Ophthalmology. This was a very, very influential book, and it was the first systematic treatment of the entire field of the relationship between optics and vision. And it was used in medical schools. He talked about a lot of things, including the anatomy, diseases, how do you treat them. He talks about corneal ulcers and how they can be treated through surgery, and so on. And he also talked about how you can repair cataracts, which is a clouding of the crystalline lens. Of course, the ancient Hindu scientists back in the 5th century had talked about cataract removal using a method called couching. I'll come to that later on. Now, probably the most influential person in the history of optics was Ibn Saul. He was a Persian, he was an optics engineer, and he wrote a famous book in 984 called On Burning Mirrors and Lenses. In that, he showed how curved mirrors and lenses bend and focus light. In fact, if you look at his manuscripts, you can see that he gave the first law of refraction, and that is shown out here. This was about centuries before Snell. And essentially what he shows is that if you have an interface, this line is the original light that's incident on the interface, and this is the bottom hypotenuse is the line that is refracted into the medium. And he showed that the relationship between them was essentially, he didn't say the sine of the angles, but he said was related to the sides. And so, but, because of the Eurocentrism, we call it a Snell's law. John Dudley, who was one of the leading lights behind the International Year of Light, actually wrote a op-ed in Physics World way back, talking about how it should be called Ibn Sal's law. So using what he had discovered, he derived lens shapes with no geometric aberrations, anaclastic lenses. He also talked about plano-convex lenses. And in fact, this is a illustration from his book. This is the planar side, and he talked about light coming in, hitting it, and coming to a focal point. And he talked about the role that curvature plays in determining focal points. He also dealt with parabolic mirrors, ellipsoidal mirrors, biconvex lenses, and how you draw hyperbolic arcs and so on. So in reality, considering the fact that Ibn Sal came up with the law of refraction almost 650 years before Snell, it should correctly be called Ibn Snell's law. Then in around 800s, Masawai, who was an Egyptian scholar, came out with detailed descriptions of various diseases of the eye. And he described in detail 48 different conditions, and he showed how you can remove a cataract using a hollow needle. Essentially, this sounds awful, and you can imagine the pain that the patient undergoes, but basically you make a incision, and then you stick this hollow needle in, and you suck out the cataract. Now, I should tell you that modern cataract surgery involves something called phacoemulsification. Phacos meaning lens from the Latin, and emulsification means emulsifying or making it into a liquid. As you know, the cataract is really, because of the crystalline proteins forming disulfide bridges, and therefore they are no longer as flexible and they scatter light. And so in phacoemulsification, what one does is you stick in not a needle, but something called a phaco tip. And what you do is you emulsify it by sending in essentially water, and you break up the cataract by having a piezoelectric crystal that vibrates at very fast speeds, and it's like a jackhammer which breaks down the cataract, and then it's sucked out. This is very similar in a way to the suction method. And the suction method was largely unknown to the Europeans until about the mid 1700s. And the ancient Indians, as I said, came out with a method called couching, which is, I suppose, even more painful than the suction method, because what you do in that is you make an incision, and then with your thumbs, you press down on it so that the cataractous material flows outside. I certainly wouldn't want to have that type of cataract surgery done. Then Masawi, of course, wrote this famous book called as I said, here's an illustration of him doing cataract surgery. And he talked about why you need to bandage the eye. Probably they used egg yolk to cover the incision. And, he talked about the many surgeries he did. Ibn Sina was the other, and he's known as Avicenna in the Western world. That's his Latinized form. And he wrote more than 200 books on medicine and science and philosophy. He further expanded on the Greeks. So again, he was a polymath, and apparently had written close to about 450 treatises or books, but only about 240 have survived, including about 150 on natural philosophy and about 40 on medicine. he wrote this famous book called The Book of Healing, and it was really an encyclopedia and something called the Canon of Medicine, which was used in European universities until as late as the 1650s. So, but what Avicenna did is very close to what we talk about in today's modern medicine, which is, for example, he classified cataracts on the basis of size and density and color, which is no different from modern cataract classification schemes that were used using densitometry. A guy called Shylock at MIT came out with this technique in the 1980s for having standardized versions of cataract classification, and that's very, very similar to what was proposed. And he also talked about the role of nutrition in cataract formation and natural conditions, the environment. And he also talked about the fact that cataract should be done only when it is in the mature stage, which is what we do in modern medicine now. And also, he also proposed that a patient's psychological status is very important in the patient recovery. So the most important contribution of Avicenna is that he believed that medication nutrition in early stages can solve a lot of problems without the need for surgery. So again, this is a picture of the eye, and this is a modern version, and this is from an ink manuscript. And you can see that, here you have the cornea, the lens is shown here, this is the iris, this is the vitreal chamber, and then the optic nerve. Now, Ibn Isa is also known as the Jesus oculist, and he's probably one of the most famous clinicians of his time. And he wrote this famous textbook on ophthalmology, which of course included optics. And he talked about over 130 eye conditions. And it illustrated the optic chiasm and the role of the brain. And it was used by Western anatomists for centuries. He also looked at other ophthalmological disorders and designed a number of different surgical tools, and many of them are used in modern surgery. So essentially what happened is, in about 250 years, the Islamic golden age of science produced more than 18 works on the science of ophthalmology, while the Greeks in a millennium produced only 5, and none by a specialist. Though the Greco-Romans understood practices, they were very crude and very little scientific basis, unlike the Islamic scientists. And the thing is, their work acted as a foundation, not only in ophthalmology, but in general of European science and medicine well into the Victorian times. So in fact, Hirschberg, who was the president of the American Medical Association, the world's largest professional society for medicine, does talk about this, and he says in a 1905 lecture that during this total darkness in medieval Europe, the Arab Muslims, lighted and fed the lamps of our science, from the Guadalquivir in Spain to the Nile in the Egypt and the Oxus River in Russia. They were the only masters of ophthalmology in medieval Europe. Now we come to the hero of my talk, which is Ibn al-Haytham, or al-Hazan. He was a polymath again. He was an astronomer, he was a mathematician, he was a civil engineer. He worked with the pharaohs to build levees to prevent flooding by the Nile River. And he made important contributions in optics, astronomy, mathematics, meteorology, perception, and what we now call as the scientific method. He was the one who put on a real strong foundation that, all science should be based on empirical evidence. In fact, he was in medieval Europe, he was just called the physicist because of his wide range of research in science, and especially in physics and optics. So, as I said, he wrote, he's supposed to have written over 92 books, but only 55 have survived. And the most important of it was called the Kitab al-Manzir, or the Book of Optics. It's probably his most important contribution, and it was translated into Latin in 1270, which influenced people like Kepler. And you see, the thing I like about what he says, let's see, where did I go? Okay, is that he begins his book that the inquiry into the principles and premises of how he will do science. His methods will involve, quote, characterizing premises and exercising caution in drawing conclusions, while he aimed to employ justice, not follow prejudice, and to take care in all that we had judged, and criticize that we seek the truth and not be swayed by opinion. Which is amazingly good advice for any scientist today. I don't read classical Arabic. It's an extremely tough language to learn, but there are two very good translations of some of the volumes of Kitab al-Manzir. And one of them is by a gentleman called Smith, who is a professor of history, I think, at Wisconsin, who translated the first two volumes into English back in the 1980s, and that's a standard handbook. And then there was another translation published by a scholar of Middle Eastern history at Harvard, and I'll talk about that later on. The other person who has done a lot of work on looking at the scientific basis of Al-Haytham's work and in optics is Roshdi Rashid. He's an Algerian-French physicist, optics person, who also has a very deep knowledge of Arabic science and classical Arabic. I've had the good fortune to work with him on a book, and he talks about the Reformation of Optics by Al-Haytham. And he basically comes to three conclusions. That is, he aimed to mathematize every empirical science. And he showed how mathematics can underlie the description of very different areas. And he also was concerned not only with optics, like I said, for every natural science. And the success of any investigation, he said, whether it's mathematical, linguistic, or technical, was by mathematics and by quantitative evaluation. So on the left, I show the first, the figure drawn by Al-Haytham in his Kitab al-Manzir. And here he shows the structure of the eye. Here is a cornea, here's a crystalline lens, here's the optic nerve, and he conceived of the eye as being made up of two spheres, one smaller than the other. And this is a modern illustration of Haytham's work by Polyak, who was a very, very famous anatomist, and from his book of Anatomy of the Eye in 1941. The Al-Haytham actually showed how the eye was an optical instrument. He did multiple light source experiments, and he did that with by discovering the camera obscura, and he showed that this gave him the idea for corresponding point projection of light from the surface of an object to an image on a screen. And so he called it was the beam chamber or camera obscura. And using this, he synthesized anatomy and optics and gave rise to a field which is now known as physiological optics. And this term was actually introduced by Helmholtz in the 1860s. Oh, I should tell you, Helmholtz, we all know about in physics, the Helmholtz equation and so on. Helmholtz was actually an ophthalmologist. He was an MD, and he worked in the Prussian army to calculate artillery trajectories. He also invented the ophthalmoscope, the optics of the ophthalmoscope, so that you can look into the eye. Haytham also talked about how the pupil is an aperture which is variable. However, the big mistake he did was, like Avicenna, he said that the lens was the receptive organ of sight, but he did say that the retina was involved in the process of vision. So this was the major problem Alhazen gave. Given a light source and a spherical mirror, find the point on the mirror where the light will be reflected to the eye of an observer. And Roshi Rashid wrote a paper in Science way back in the late 70s, which delved into great detail about this. And in fact, this book, this problem was actually given a good solution by Christian Huygens. And in book 5, Haytham talked about cylindrical and concave mirrors. And then in book 6, he examined the errors in optics and due to reflection and refraction. So basically, what he does is he does not say that is how to give a mathematical expression for the law of refraction. However, what he really did was he explained it as being due to the idea the light is a movement that travels with variable speed, lower in a denser medium. And because of his studies of refraction, he proposed that the atmosphere had a depth of about 15 kilometers, and he was able to explain twilight by the refraction of sunlight. And so in all these ways, he kind of looked at and foresaw what modern science does. And the way he proved the extra mission theory was doing very careful experiments and used the idea of after images. And he also showed that, showed that if we had the extra mission idea, we should be able to see stars during the daytime. And he said, no. And he showed why it is so, because he came up with the idea of contrast. So, and his basic conclusion was all things that, indicate that light produces some effect. And so here is this picture from the Latin De Astibus, which shows his camera obscura. And he also shows in book 2 that visual perception and a lot of the ideas he gives in that book, we have only rediscovered in the 20th century in the study of vision. He also comes up with certain things which for example, in computer science, we now call as k-means clustering, even though he didn't give an exact mathematical formulation of it. He basically talks about it. Oops. So this is these are the 3 greats of ancient science, Galen, Avicenna, and Hippocrates. And as I told you, it's the extra mission theory that for once and for all, Haytham proved. And therefore, he married optics, physics, and physiology. But in his idea of the eye, this again is a figure from his book, he did not apply the ideas of the camera obscura in terms of image formation. Now, as you know, in a camera obscura, you get an inverted image. So why do you see things being upright? And that was a problem that was not solved for a long, long time until Kepler gave a reasonably good answer to that question. Now, I'd also like to emphasize that, we have something called Occam's razor. It's named after the Earl of Occam. And basically, Occam's razor essentially says, if you got a number of different explanations of a phenomenon, the simplest is the best explanation. And in fact, Haytham gives a form of Occam's razor and says that, and he uses that to show that particles of light coming from the eye are an unnecessary complication. It's not necessary to understand the process of vision. And the other major advance that he did was this. He also formulated that once the image is formed, which is the area of physics, he said, now it is all due to psychology in terms of how you perceive it. And in fact, it was Kepler who later on, showed that the eye was like a camera. But Haytham had put in the idea of a pupil as an aperture and used various ideas that he had in order to show the importance of the retina. Now, the eye as an optical instrument was given by Helmholtz in a famous treatise published in about 1860 called Treatise on Physiological Optics, which was later reprinted in English by the Optical Society of America in the 1920s. Helmholtz basically, in an encyclopedic form, talked about both the various visual processes, the anatomy and optics of the eye, and he borrowed very heavily from Haytham. So remember I told you that Haytham dealt with how the eye was, say, two spheres, and he talked about how you can talk about descriptive anatomy and functional anatomy of the eye. This forms the basis of eye models that we still use. On the left is a wide-angled eye model that I developed sometime in the 80s. On the right are, and these eye models are called schematic eyes, and they are still used in doing various types of calculations. If you want to put in additional optics, what would the retinal image be, what would be the magnification be, and so on. And in fact, Gullstrand got the Nobel Prize in Physiology and Medicine in 1911 for his formulation of these simple spherical eye models. Like I said, now there are much more complicated eye models. The Gullstrand models work only under the Gaussian approximation. Like I said, there are wide-angle eye models. There are eye models that correct for chromatic dispersion, for spherical aberration, and so on. So this is the basic idea of Haytham. You have a smaller sphere, which consists of the cornea. Then you have a lens out here, and then you have the larger sphere, which is the retina with the optic nerve coming out of it. And this is our modern idea, and we talk about a visual axis, which Haytham even drew as a line perpendicular to the center of the cornea. And as I said, he correctly stated that once the light was received in the light-sensitive layer, which he incorrectly thought was the crystalline lens, he said, strictly optical considerations do not apply. He said there is an isomorphism between the object in space and its projection on the retina. This is a point-to-point correspondence of the visual world, and this is one of the modern basis. This is one of the bases of modern visual science, that the visual system does a punctiform analysis, and this can be shown by very, very interesting recordings done in the visual cortex by De Valois and others at Berkeley in the 1990s, where they essentially showed in alert macaques patterns like this, and the monkeys were whatever your ideas on animal experiments are. That if you look at, if you do histology of the visual cortex, which had been injected with 2-deoxyglucose, radioactive glucose, then it should light up, meaning that the cells that are processing it will require more energy. And when they do the histology for a pattern like this, if you just look at this part hemisphere, you see this is how it's represented in the visual cortex. Now, it is not exactly, except in the central region, it's not exactly an isomorphism. However, Eric Schwartz at NYU later was able to show that what you really find is a conformal map of what is out there in the world, which is mapped onto the visual cortex for areas away from the center. Now, in book 1, Haytham also talks about additive color mixing, the RGB space that we use in our monitors. He talks about how you should have certain basic colors and you can create other colors. He also discusses how color, our perception of color depends upon the luminance of the object. And this happens because of the duplex nature of the retina. We got two types of photoreceptors, cones and rods. Cones work at very high light levels, which is where you see color, and rods work at low light levels or scotopic light levels. And in fact, in this figure, what I show is the scotopic light levels, which show rods under what luminance levels and where the cones come into operation. And then he showed how your vision depends upon the light level, which we do know. You know, when you go to an optometrist or ophthalmologist and you measure your acuity, that's measured under photopic conditions at high contrast. However, at low contrast or at low light levels, your vision really decreases, and Haytham recognized it. He also, he recognized the role of contrast in vision, and he used this argument of contrast as to why you don't see stars during daylight. And he also said something which we now call as simultaneous contrast. That is, the color of an object depend upon the surroundings. Now, this is a very famous example of simultaneous contrast. If you look at this, these gray squares all have the same luminance value. You can take a photometer and measure its CIE coordinates, but they appear different to you. Some of them appear darker, more saturated than the others. This is simultaneous contrast, and Haytham knew about it, talked about it. This is an area which is close to my heart because it talks about directional sensitivity of photoreceptors. It's also called the Stiles-Crawford effect, and in fact, this is due to the fiber optic nature of photoreceptors. And in fact, Professor Gatak in the audience has worked on it. And I've done work on the Stiles-Crawford effect, both theoretically and experimentally. And what it really says is that light coming through the center along the pupil, along the central axis, will appear brighter than light coming from the periphery. And Haytham basically talks about this. He says that refracted rays lose their power to stimulate the sensitive organs if they come from peripheral. And that's the Stiles-Crawford effect, which was measured by Stiles and Crawford, two physicists in England in the 1930s. So essentially, light rays coming normal to the surface of the retina are more likely to be detected than light rays that are oblique. Again, it goes back to your optical fiber or waveguide and how it captures and launches the incident light. Okay. Contrast sensitivity. Even though Haytham did not know about modulation transfer functions, what you're looking out here is I'm changing the spatial frequency of the sine wave gratings along the x-axis and the contrast along the y, going from low contrast to high contrast. And most of you or all of you will see that you don't see everything equally. You see kind of like an outline of an umbrella, a U-shaped thing. This is essentially the modulation transfer function of the human visual system. Now, the MTF, the modulation transfer function of the human visual system, is related to the contrast sensitivity function is related to the MTF, but not quite, because at low spatial frequencies, there's a reduction in your sensitivity, which is unlike, say, if your eye were a pure optical instrument at low spatial frequencies, your MTF is going to go to 1, which you do not find. And this is due to the neural structure. Haytham worked on binocular vision, and he developed something called, developed a board by which you can measure very small differences in stereopsis, which is your ability to detect distances in depth. And the reason that happens is because the two eyes are separated horizontally. And light from a point should fall on what are called corresponding points in the retina. And the corresponding points, if they don't fall on corresponding points, you will see double vision. But if they fall on corresponding points, you'll see things as being whole. And this was actually investigated by German Panem back in the 1860s, 1870s, and he came up with something called Panem's fusional areas, and he showed why this is so. So this is called binocular correspondence. However, Haytham had actually foresaw this, and he essentially talks about Panem's areas. So he says that every pair of points, two similarly situated points in the eyes, will proceed to a single point among the surroundings along the common axis, which is our modern explanation for stereopsis. Now, when you're talking about stereopsis, we come out with a non-Euclidean object called the horopter. Only points on the horopter, as you're looking at something, is going to appear as fused and single to you. You have both a horizontal horopter as well as a vertical horopter due to the shear of the photoreceptors. This is very, very important because when people create virtual reality devices or artificial visual devices, you need to take into account this idea of the horopter and incorporate it into your optical design. And Haytham has anticipated the idea of the vertical horopter and the longitudinal angles which are used to analyze the horopter. Another important aspect of that Haytham did, which he again talks about, is the role of the extraocular muscles in moving the eyes. In fact, Haytham basically states that the eyes should be moved to bring into focus different objects in the region of highest, clearest vision, which is the fovea of the eye. And Haytham basically says we build up this vision as we gaze over a scene. And what is even more interesting is to look at this eye movement there are 6 extraocular muscles that can move the eyes in horizontal, vertical, and oblique directions. He used mechanical analogies to talk about how something can be moved. And this is very similar and is the basis for the Hamiltonian or Lagrangian optics or in classical mechanics. So he also described something called Listing's law, which again, a German scientist, Listing, described in the 1880s, called Listing's law, which basically says that the eye is kept rigidly in place, and the only motion that's proper is rotational motion, up or down or side to side. And this is nothing but a descriptive statement of Listing's law. He also comes out with something called equal innovation, which was actually described, which is now attributed to Descartes. What it really means is the following. The innervation, the signal from the brain that makes the eyes move, are the same for both eyes. So if one eye moves to the right, the fellow eye will also move to the right. So it's called equal innovation or reciprocal innovation. So, and essentially, Haytham describes it. And he also says that if one eye is blind, even if the other eye moves, the blind eye will also move. And that's how we prove this reciprocal innovation idea. So this idea of eye movements is very important. In fact, Haytham does talk about why eye movements are very important and about scanning eye movements. He basically says how important eye movements are for you to be able to see. And a good example of that is something called the Troxler effect. If you keep staring at something, a small object, what will happen is the visual system will adapt to it and it will fade from view. So you always have to have these, even if you're fixating on something, if you're looking at something, your eye continuously does very fast microsaccades and drift and tremor. And back in the 1990s, I wrote a paper showing how these drifts and tremors obey a Langevin type differential equation. It's a stochastic differential equation, and experimental data supports it. So eye movements are very interesting. And so if you look at this picture of Nefertiti, Alan Yarbus was a biophysicist in the Soviet Union in the 60s, actually mapped out how eye movements are done. You don't look at the whole figure, but you look at points of which have the most information, which means points where there is a edge or a change in contrast or things of that sort. And to do that, you make these very fast saccadic eye movements. And a teacher of mine, Larry Stark, who was a biomedical control engineer, actually showed that these movements are time optimal. So what he did was he applied control systems theory to show that any saccade you make is a time optimal saccade, and it obeys what is called bang-bang control. I won't go into it, but that's what it is. In book 2, he also talks about various different things. He talks about size constancy. Why do things, an elephant at a distance looks like an elephant, and you see it as an elephant even closer, even though the angular subtend subtended is different. And he showed, for example, color constancy. What is color constancy? Let's say that you take a rose out in sunlight inside, and the light source is a fluorescent light, you know that the spectral distribution of the light is different, but you still see the rose as red in color. That's called color constancy. And Haytham seems to be the first one to record color constancy. Now, he also talks about depth cues. What are depth cues? Again, this is very, very important in three-dimensional displays, in virtual reality devices and all that. Now, paintings, how do you see depth? For example, in this painting, where even though it's a two-dimensional image, like this couple are in front, that you're going into the distance and so on. That's because the artists use what are called monocular cues to depth, which includes things like texture. It includes what is known as the ground plane. What that means is objects further away will appear higher in your view. That's the ground plane, which is again used in 3D displays. Texture gradients are very important. Size constancy I told you about. This is a very, very famous illusion called the Ponzo illusion. And you've all probably seen this. The length of these two bars are the same, but the bar behind appears to be longer than the one in front. That is because your visual system is playing a joke on you. It takes into account these visual cues. You know that parallel lines like these railroad tracks, as they go into the distance, seem to converge. And then then you got all this texture. Close by, you see all the individual little stones, but as you go further out, it smoothens out and all that. So your brain thinks that the bar behind, even because it subtends the same visual angle as the bar in front, but it's at a greater distance, it has to be larger. That's called size constancy. And the moon illusion is something which is probably the oldest known visual illusion in humankind. In fact, in the 7th century BC, in Babylon, it's recorded. And you've all seen this. What it is the rising moon, or the setting sun, for example, at the horizon will appear to be much, much larger than the moon at its zenith. Now, if you actually look at the visual angle it subtends, it's about the same. It's about 1 to 2 degrees of visual angle. How can I show it? Your thumb at arm's length subtends about 1 to 2 degrees. And with your thumb at arm's length, you can block out the rising moon or the moon way up above, showing that it has the same size. But why do you see this as being so big? And it was Haytham who showed that this was due to the subjective nature of perspective, and it is an optical illusion. The ancient Greeks, like Ptolemy and others, thought it was magnification effects caused due to a refraction of light in the atmosphere. No, but it is your brain playing jokes on you. And in fact, Irwin Rock, who was a very famous cognitive scientist at Penn State, which is where Akhilesh is at, in the 1950s, gave the complete explanation for this phenomenon. So Haytham was quite a pioneer in all of this. In terms of optics, in terms of optical systems, he defines the optical axis, and he talks about the eye as being a centered optical system. That's not really true. The eye is a decentered optical system. And well, I won't go into why that is so. He also talked about something called visual attention. This is a very high order analysis done by the brain. And he says that a series of logical inferences must occur before sensation can be changed into perception. And he also said that the speed of perception is extremely fast. And in fact, Helmholtz reformulated this as a theory of unconscious inference. And this is the basic idea of modern cognitive science. And in fact, Haytham's statement that the time required to perceive something has become a major method for analyzing unconscious inferences that underlie perception. What we now do is study reaction times in milliseconds. We also study what happens in the brain by looking at functional magnetic resonance imaging. Again, we know from fMRI and other studies, visual processing occurs followed by a series of very complex interactions. So it goes from the retina to what is called the lateral geniculate nucleus to the primary visual cortex and to other higher areas. And this is, Haytham did not know about all of this, but he said that essentially you look at initial image, and now in modern terminology, we call it pre-attentive vision. That's the impression that is formed of the visual stimulus, and then impressions are formed at higher levels of processing, and that's your unconscious inference. So now the greatness of Haytham is not that there's a law named after him, like Einstein's law of gravitation or Helmholtz's equation, but it is in the way that he taught us to do science, to study science. In that sense, the way he said about logical inference based upon empirical data and all that, you can say that he's the founder of the scientific method. I mean, we normally ascribe it to Francis Bacon or Descartes. So essentially, what Haytham did was turn experimentation from a general area of investigation to a standard means of proof of scientific theories. And so based upon that, using this scientific method, he came to conclusions. And that is his legacy for science, and especially for Western scientists. So again, this just, I do want to emphasize that Haytham in his work on optics enunciated many fundamental principles which are credited to scientists, especially European scientists, in the last 200 years. And he synthesized physics, mathematics, and physiology and anatomy, and he developed great insights into the psychology of perception. He also did things like what we know as clinical tests of vision. So there are a number of questions, which is what inspired early scientific effort in the Islamic worldview? What obstacles are confronted in its progress as centuries passed? What are the factors within and beyond Islamic lands contributed to the eclipse of Islamic science in, and European science took over? What was the extent of this enterprise? How did it influence the development of science today? And what lessons can we learn from history about the rise, decline, and fall of great powers and intellectual development? What is the role of religion and faith, if any, in the development of knowledge? And lastly, is our search for knowledge about the universe adequately served by what we have long considered as a scientific method? For example, one of the common things we do is, in all of natural sciences, we linearize phenomena. Most of the, if not all of the equations of science, of physics are linear equations, but we do know nature is nonlinear. Since we cannot solve nonlinear problems, we linearize it. And this is where theories like chaos and wholeness comes in, completeness. And for more of this, this is my book, which I worked with Roshni Rashid, this deals with it has a number of different chapters dealing with different aspects of Haytham's work. And this is a volume in a series I edited. And if any of you are interested in contributing to the volume, let me know. And thank you so much. So if you want to look at Haytham's books, I told you a Harvard scholar Sabra translated books 1 through 3 in English with commentary, and then of course Smith's book, which was published by the American Philosophical Society in the 80s. And then my chapter in that book, it's about a 70-page chapter that goes into various aspects of what I've spoken about. I've only given you a general bird's eye viewpoint of the work that has been done. So anyway, thank you for your attention. I'll stop at that. Okay. Questions, comments? Hope I didn't bore you too much. Yes, sir.
Thank you very much, sir, for such a nice talk. Really, it was mesmerizing. So maybe we will forward it to other students also who didn't attend today, or maybe from other departments. Thank you very much, sir.
I would also like to refer you to what is that? I'm sorry. There was some noise.
No. May I say here that this is actually very good attendance, because there are 9 students present and 1 super student present, Ajay Ghatak.
Right. Well, you know,
I really enjoyed the talk. Vengu. Thank you for letting me know.
Thank you. As you know, history is another one of my areas of interest. And I mean, I've done a lot of work on optical history in modern or Renaissance science, but I was really fascinated when I went into studying Haytham. And recently, last year, there was a book published called Horizons, and Horizons deals with the results of non-European science, for example, in South America, in the Polynesia, of course, in the Indian subcontinent and elsewhere, that have played a major influence in European or Eurocentric science, to which we give credit to European scientists. And that's a book well worth looking at. It's called Horizons. Okay.
I was thinking about this Alhazen. I became familiar with some of his work in about 1986.
Yes.
When I went into the history of the Brewster angle.
Oh, yes, of course. Yeah.
The Brewster angle was unknown to Brewster. Today's Brewster angle was unknown to Brewster.
Right.
Okay.
Right. Polarization as such.
Yeah, right.
It was known much earlier.
You couldn't have known.
Tell me briefly about that. Briefly, 1 or 2 lines about the Brewster's angle's history.
Well, Brewster could not have said that there was a 0 reflection angle. Impossible for him to say. Okay. All he could have said, and he did, and I have actually looked at his 1812 paper, is that it was a polarizing angle.
Right.
Okay. And with the emergence of lasers, polarizing angle was completely forgotten. Okay. You don't even find it in many textbooks today. Okay. And it is given as a 0 reflection angle. And it turns out I was looking at reflection by a chiral material, a chiral half space, and there was no Brewster. I couldn't find a Brewster angle as conventionally defined as taught to me. Okay.
Okay.
And yet, when I looked at a book by Hollis Chen, there should have been a Brewster angle.
Mm-hmm.
Okay. And yes, it was then easy to find it once you realize that Brewster angle is actually not the 0 reflection angle. That's a corollary rather than the theorem. Okay. But it is a polarizing angle. And then from that, you can actually extend the idea to that in any material, I'm assuming half spaces here. Okay. There are 2 polarization states possible. Waves are 2 polarization states possible. And the ratio of the amplitudes of the incident waves is independent of the ratio of the amplitudes of the refracted waves at what may be called the Brewster angle, but should probably be called Brewster wave number.
Hmm.
Okay. And it completely gives you a different perspective. So anyhow, Haytham, I became interested in them, and I actually submitted an article to Optics and Photonics News in those days, and they
Okay.
published it. And they asked me, they wanted to put some picture, and I said, which picture to find? You know, in those days, libraries were not that easy to get into.
Yeah. Mm-hmm.
Very difficult. I happened to have a stamp issued by Pakistan on Haytham, the father of optics. And then I got hold of that stamp, blew it up. That fortunately was possible in those days. And then they actually reproduced it on the cover of OPN. So that was very nice.
That's right. You're a philatelist. I forgot about
Yes,
that.
I'm a philatelist. Yeah.
Yeah. Right. Actually, going back to that, the ancient Vikings knew about double refraction.
Yes.
Okay.
Yes.
So, I mean, there's a lot of stuff that has been rediscovered, but not properly attributed to.
Yeah. Oh, and Ibn Sahels was something interesting too. I don't know exactly how I came to know, and then I found Roshdi's paper.
Yes. Okay.
Okay. Roshdi's paper, and I started writing it in my Beltrami Fields book. It is called Ibn Sahels Law. That was 1994.
Yes. Yeah.
I started calling it that. But nowadays I don't. I actually refrain from using names because people get very nationalistic about various things.
Exactly.
So it should simply be called the law of phase matching.
Mm-hmm.
Yeah.
Yeah, I mean, I had the great fortune to work with Roshdi Rashid for over a year and a half, and he's an amazing guy. He's pretty old, but he has done a lot of work in bringing to light a lot of the ancient Islamic science.
Yes.
Yeah.
Tengu, Shweta has a question. Shweta, Prof.
Okay. Yes, please go ahead.
Thank you, sir, for such a nice talk. Sir, I just want to ask that in India, in ancient time, means before the era of Islamic, means medieval era, Sushrita was also performed the surgery of cataracts. I want to ask that Sushrita is means before the Islamic means or after the Islamic surgeon which performed the surgery for the cataract.
Oh, yeah. I mean, cataract surgery is probably the most widely done surgery in the world. Okay.
Yes,
Just as Benjamin Franklin said, there's nothing in life, nothing is certain in life other than death and taxes. One can also add cataracts to it. All of us are going to get it, okay? And cataract surgery was known even way back in the time of the Egyptians, except that obviously it was an awfully painful procedure to do. The Indians Sushrita did it back in the 5th century using this couching technique. So it's not like we don't know what happens with the cataract and that we should take out this opaque substance. Is that your question? Or did I misunderstand your question?
no, sir, you well said. Actually, I just means Sushrita. I have read in the literature that Sushrita is known as the father of surgery in the world. So means he's very earlier before the Islamic era.
Right. Okay. I understand what you're talking about. I think there's a little bit of nationalism involved in it because there are examples of surgery even much beyond that, way back. Okay. It might not have been systematized, but there are examples in history of surgical procedures. Okay.
Okay. Thank you, sir.
I've just put on chat 2 papers on Sushrita and cataract surgery history. for
Mhm.
those of you who are interested.
Okay.
Okay,
Yeah.
sir.
Anything else?
So there's something which has always not always, I would say, fascinated me in the last about 10, 15 years. See, Vengo, what do you think of that? Let me ask you the question. There is no doubt in my mind that the civilizations in India, or South Asia, let me call it more generally.
Yeah,
Okay. Yeah, it's better to call it South Asia. Were very advanced in many, many different ways, many technological fields, far ahead, certainly far ahead of the Europeans. There was no doubt about it.
Yeah.
No doubt about it. Okay. And in some manner, they were co-equal with Egyptians or Sumerians or the Babylonians at different times. Okay. What, in your opinion, happened that South Asia lost its technological edge, let us say around the year 1080, approximately?
Well,
And a parallel question is, what happened to the Arabs about after the Battle of Lepanto, 1571? I mean, scientifically, they became Gober.
right. I mean, you raised two very, very good questions for which we don't really have good answers, because it's almost like Islamic civilization that's spread out over such a vast area of the world, which gave us all of this, just suddenly seemed to come to a screeching halt. And in terms of South Asian civilizations, I think a lot of it is because they were not written down.
I see.
Okay, at least that's my impression from reading, from my reading. But you don't find a lot of information of what they did. We do know not just the